Hey everybody, welcome to the AP Calculus Unit 2 review. This unit is on the Introduction to Differentiation, where we discuss the definition of what a derivative is and its fundamental properties. So before I begin, I want to kind of give like a little disclaimer. Again, I am making these videos in a way that's like, I'm proving things to you, I'm showing you why things work and all that kind of stuff. I will go through one or two examples during this video, but typically I'm not going to do that in other videos. Just giving you an example just so you actually know what you're doing. And so I'm giving you like the foundations you need. So if you want more practice, which you should definitely do, make sure to find some practice problems online. I have a bunch of other videos that you can watch. My Ace Math review series could help with that kind of stuff too. That's one of my playlists that you can watch, where I run through some other problems and exercises. So, derivatives are something that you definitely need to practice. You can't just like watch this one video and be like, oh, I'm good, I'm gonna ace all my AP exams, You have to definitely do a lot of practice. So just with that out of the way, let's begin. Okay. First thing I want to say is I'm repurposing this little space down here. I'm just going to kind of like put what the actual topic is, like what we're, like the section of the video. So the first section is building intuition for what a derivative is. So I want to talk about the words, a derivative versus differentiation. Differentiation is the process of taking a derivative. Now, what is a derivative? Really, that's just a slope of a function. So here I have three graphs, okay? I just want to focus our attention on these two. Here, if you know some algebra, which I hope you would if you're watching a calculus playlist, you should know how to take the slope of this. If you have like an equation or something, you can definitely do that. You can kind of estimate this to be about y equals x minus 1 or something like that. So this is pretty easy. So the slope is just about 1 because it goes like up 1 over 1, up 1 over 1, something like that. So we know how to find the slope of this, or in other words, with our new vocabulary, we know how to take the derivative of this, or we know what the derivative is. We don't know how to find it. We just know what it is. It's about 1. But here, how are we supposed to find the slope of this? Like the slope is always changing. And previously you couldn't do that, but now you'll be able to, and especially after you do some practice, you'll be able to. So we're going to find ways to find the slope of a function at any given point. And so you might be thinking like, well, how can we do that? Isn't a slope just a number? How can a number, like the slope, let me use something like this. The slope here at this point here, it's not really, okay, well, I'm not going to use that. The slope here is different than the slope, I don't know, up down here, right? It's obviously different. This is positive and this is negative, and so that's really weird. And so you're not, the number, you can't have a number as your answer. So how do we do that? Well, our slope is going to be in the form of a function, okay? And that will allow us to, have different values for different slopes for different values. So that's really going to help us. And so let's figure out how to do that. So we can definitely find the average slope between these 2 points. We would just draw a line. Oops. Draw a line. Hold on, I need a new marker. Alright, so we could definitely just draw a line. Let me make that line a little more clear. There we go. Just draw a straight line between these 2 points. Compare their slopes like you would here, and boom. Or compare the, you know how to find the slope. And boom. But like, how do you find what we call instantaneous slope, or the instantaneous rate of change? Basically, we're gonna figure out how to do that. So let me actually use the same graph here. So let's say we want to find the slope at about, I don't know, this point here. So what we're going to do is we're going to fix this point here. We're gonna keep it there. And we're going to have some other point. Let's say it's like over here, right? And we're going to be able to move this around. So let me say this point down here is going to be x, comma, y, or in a more general, or not a more general, but like a more like rigorous context, we're going to say x comma f of x, right? So x comma our input, or like we put it into the function. While over here, I want to call this point, well, it's x, it's x plus a little bit, like a little extra. We can call that little difference h. And then our f of x is going to be, if we plug that into our formula, it's going to be f of x plus h. So let me show you. Let me put it up here. So we're going to have x plus h, and basically that just means it's this point, but just a little bit, like a little extra difference. And then we're going to do comma f of x plus h. We're going to input that same thing, right? And so I'm going to label it, I'm going to show that it's this one, and then this is this one, right? So we have this fixed point, and then we have this variable point with an h that we can choose. So if we want to find the slope between these 2 points, we can definitely do that, right? We can find it, and that's going to be, we can just say f of x plus h. So we can say this is going to be f of x plus h minus f of x, so our two y values, over x plus h, and then minus x. So I hope you see how I did that. I just did this minus this over this minus this. Your standard way to find your slope. And you can see that this x minus x is just going to cancel out. So I can just rub this out. And then we get f of x plus h minus f of x over h. Basically saying your function with a little extra minus your original function. So this is just a difference. This is like your delta y divided by h. And h is that little difference, your delta x. So this is like your delta y over delta x, your change in y over change in x, your average slope formula, right? But this tells us the average slope, right? We want to find something that's basically, we want to find the slope at a certain point. But let me, think about that for a second. A slope is a rate. It's a rate of change. You can't have change or even a rate with just 1 point. You need 2 points for that. And so how can we make it so that we can find the derivative at 1 point, but we use 2 points to do that? Well, that's if we put both points infinitely close together. And that's what we call a limit. So we're going to say this difference h, so actually let me say up here. So we're going to move our variable point closer this way, and we're going to move it so that it's basically touching that other point. So I'm gonna make that a little bolder, right? And so it's moving closer to that original, that fixed point. So our h, our difference h it's becoming very, very small, to the point where we're not quite at x comma f of x, we're just very, very small, like a very, very, very close. So it's a very small difference. So we're gonna say that the limit, we're gonna use our tools from last time because, calculus builds on itself. The limit as h approaches 0. So this little difference between these 2 points is going to 0. And so it's basically the limit as h approaches 0 of our slope. And we call this f of x, but not just f of x, right? Because f of x was our original function. This is f prime of x. That's an apostrophe, not a 1, it's an apostrophe. And what this means is this is the derivative of f of x, of our original function. And this is how to find that derivative. Okay, that's really interesting, right? And so that's going to give us a way to find the derivative at any point. Okay, so let's think of a function. Let's say x squared. That's a pretty good function. So let me give an example here. So we're going to say f of x is equal to x squared. And then there are different ways to phrase the question. You could say, find the derivative of, and they could say f of x, they could say x squared. I'm just going to write of, of x squared. Let's just say this. They could also say find f prime of x if they actually give you the function. So find f prime of x. So find, if f of x is x squared, find f prime of x. So find this. Or they could say find and I'm going to use some more notation here, d divided by dx of x squared, and I'm going to put this in parentheses, and boom. So these are three different ways of asking the same question, and they're all asking the same thing. So what is this d over dx here? That comes from, I'm going to put it over here, this is known as dy divided by dx. And this is your derivative of y, or f of x, another way to say it. And this is similar to our notion of delta y over delta x, right? From algebra. This is the change in y over the change in x. This means the same thing. The only difference is that this is basically this, but very small, like a very, very small scale. So dy dx, or dy divided by dx, is just a very small change in y over a very small change in x. So that's basically what it means. And so whenever you have like this d dx, like without this, basically your y, so let me actually erase this too, your y can also be down here, right? And so let's say if our y is just x squared, you can just replace that. So you have d dx of x squared. And so let me just do that. So yeah, that's different ways of saying the same thing. It is a little confusing, the notation. The reason why there's different types of notation is because there were different people that were inventing calculus in the 1700s, basically at the same time, and so they came up with these different notations, and they both became popular notations. So, you know, it can be confusing sometimes, but certain ones are better than others in different contexts, so, you know, it's more convenient in some ways. Okay, so we're going to find the derivative of x squared using our definition of a limit. And so we know how to work with limits. I hope you did some limit practice after the last video. And so, okay, well, we can just start. So let me do it over here. I can actually just draw a line. That was not very straight. Okay, so whatever. Okay, so if we have our function here, so if f of x is x squared, then we can say f prime of x is going to be the limit as h approaches 0 of, okay, f of x plus h, this is your function at x plus h, so this is going to be x plus h squared, so x plus h squared, okay, and then minus our original function. I'm going right up to the edge, but hopefully you can still see it well, and then we're dividing this by h, okay? So we're taking our original function, and we're doing f of x plus h, which is just x plus h squared, and that's going to be minus our x squared, so that's just pattern matching here, and divided by h. We don't plug anything in for h will go away on its own. So I'm assuming you probably did see this formula in like pre-calculus. If you didn't take pre-calculus, then you probably didn't see this formula, so it just depends. But this is basically that. Okay, so now what we do is I'm just going to write it over here just so we can save space. We're going to FOIL this out. X plus a squared, that's going to be, we're going to start with x squared, right? And then we're going to do, and then you FOIL it out, so you're going to get an xh plus another xh, so that's going to be a 2xh, so we add that. And then we have an h squared at the end. And then we still have that minus x squared down here, so we're going to do minus x squared, and then we still divide by that h, right? So this is just the same thing here. I just FOILed it out, and we're done. Okay, so now we just do some simplification. So, well, this x squared here, I wish I had a different color, but this x squared here cancels out with this x squared here because that's a minus and that's a plus. Okay, oh, and actually, don't forget this part. Limit as h approaches 0. Almost forgot that. That can make you lose some points. It actually will if you forget that, so don't forget that. It's really easy to forget, so just don't. Okay, so this is the limit as h approaches 0 of, okay, so then we have 2xh plus h squared over h, and so each of these have an h, so we can just cancel out an h, and this one of these h's goes away, the other one stays. So this is the limit as h approaches 0 of, well, I mean, we just have this 2x plus h remaining, and if now we can actually plug this in. The reason why we couldn't plug it in earlier is if we plug in 0 earlier, we get f of x plus 0, which is just f of x minus f of x, so that's 0 at the top, divided by 0. So we get 0 over 0, which is like, oh, that sucks, you know? But it's actually good because you're kind of, you know, if you just directly plug it in, you're basically saying, oh yeah, they're the same point, which they're not, you know? So this way you have to do manipulations, which is fine, you know, just get rid of the h's and boom. Okay, so now our final answer, as this goes to 0, we can basically cross that out as we evaluate the limit, and we get 2x. Oops, let me write that a little clearer. 2x. And this is our answer. That was really easy. Well, I mean, not easy, but like, we're done. We found the derivative of x squared. Now, you might be uncomfortable with this, like, you know, you have a slope. Isn't the slope supposed to be a number? And we got 2x. What? Well, this is interesting because now, if we want to find the derivative at a certain point, the slope of our original function at a certain point, we just plug that number in here. So let's say we want to find the derivative at x equals 0. So we can say f prime of 0, so f prime of 0 is equal to 2 times 0, which is 0. Or maybe we want to find the derivative at 5, at x equals 5, so we can say f prime of 5 is, well, 2 times 5 is 10. So this is the slope at 0, and this is the slope at 5. Now let's make sure that makes sense. So if we have a parabola here, at x equals 0, your slope is, the tangent line is going to be basically 0. But at x equals 5, which might be like up here, you have a pretty steep slope, and that's about 10, right? So, this makes sense, this checks out. So it's always good to make sure that your answers make sense, test a few points and all that kind of stuff. Okay, so now, well, I have a third graph here, right? Why do I have a third graph? Well, that's because there's yet another formula that you have to know. But don't worry, it's not too bad. It's just another way of showing this, and we're just going to briefly go over that, and then we'll get into the rest of the video. Okay, so here I have another formula. F prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. What does that mean? Well, if we look over here, basically this part is just another way of representing this. So a is just a number that we want to find our derivative at, and in this case, x equals 1, right? So that's what our a value is going to be. So in this case, a comma f of a is our fixed point, so we're moving our x comma f of x closer this way, right? So we're moving it closer this way, so let me just write the arrow that way. So we're moving x comma f of x toward a comma f of a, and then we're using our slope formula again, so we're saying f of x minus f of a over x minus a, writing that there, and we're saying that x is approaching a, it's getting closer and closer to a, so we're saying limit as x approaches a of our slope formula. So in this case, we want to find the derivative of 5x at x equals 1. We just do that. So let's say f prime of a, because this is our function, 5x is our function, so f prime of a in this case is 1, like I said. So f prime of 1 is equal to the limit. Remember, always put the limit as x approaches 1. Remember, a is what you're substituting. Limit as x approaches 1 of f of x, you just write your formula, 5x, and then minus f of a, which is going to be f of a. So it's going to be 5 times 1 in this case, which is 5, so 5x minus 5 over x, because you just write it there, and then minus 1, right, our a value. Okay, so this is pretty easy, because now we can I hope we can see that this is going to be limit as x approaches 1. We can factor out a 5 from the top, so this is going to be a 5 times x minus 1 over x minus 1, and we can cancel this with that, and we're left with the limit as x approaches 1 of 5, and that's just going to be 5. And this will always give you a number, because you're saying that x is going to a number. In this case, it's 1. Usually it's a, which you would replace with your number. So this is always going to give you a number because you're finding the derivative at a point. And remember earlier when we were using the other formula with the h, that gave you a formula. But if you want to find the derivative at a number, at a certain number, you could just plug that into your derivative formula. Both ways are completely acceptable. Now, I'm not sure, maybe they might, on the exam, they might ask you use a specific formula, in which case you would have to be knowledgeable of both formulas. Okay, so that is our understanding of our differentiation stuff here. So these are our two formulas, and I'm going to make the decision now to just stop the video here, and I'll release the second part pretty soon. I don't know if it's going to be like next week or the week after or whatever, but this is such a large unit that I'm going to split it up into two. So building intuition was like part one. Part two is going to be more about differentiation. And so we're going to talk about differentiability, and we're going to talk about the derivative rules, and we're going to go through an example there. So hopefully you enjoyed. Thank you all for watching, and I will see you in the next video. Bye guys.